Good morning, students. So today we are going to see the topic consensus and agreement. In Unit 4, the subject code is CS8603 distributed system. So first we have to know what is consensus problem. So in consensus problem, all the processes propose the values and all should agree on one among these values. For example, if we have 10 processes, so 10 processes are proposing some values. So each may differ by value or all the processes may propose the same value. But anyway, at the end, we have to agree with a single value. This is called as consensus problem. So it is mainly used in distributed computing to solve many problems. Example, total order broadcast, atomic commit, terminating, reliable broadcast, etc. So what are the assumptions we have made in agreement algorithms means the first one is failure model. So if we have n processes in the system, then you can allow f processes can be a faulty processes. So you cannot exceed the number of faulty processes beyond the value f. So we may use various failure models. So example, we may go with fail stop model, send omission model, receive omission model or Byzantine failures. So in a fail stop model, a process may crash in the middle of the execution. So what is Byzantine failure model means here the processes behave arbitrarily. The second assumption what we have made is synchronous and asynchronous communication. So in a failure prone process, for example, we have one failure prone process and that process needs to send a message to process PI in the middle, that process gets failed. So in this case, PI cannot detect the non-arrival of the message in an asynchronous system. That is, if we use the asynchronous system, if one failed process sends the message to some non-faulty process, that non-faulty process cannot detect the non-arrival of the message. So this is happened in asynchronous system. So that's why we feel the impossibility of reaching agreement in asynchronous system. Whereas in the synchronous system, easily the recipient may detect the unarrival of the message at the end of each round. So here the receiver should deal with the non-arrival of the expected message. And the third assumption is network connectivity. So we are assuming that the system has full logical connectivity. That is, each and every processes can communicate with any other process with the help of the message passing. And another one assumption is center identification. Every process in the system receives a message, always knows the identity of the sender process. In every message, you should include the identity of the sender. The next one is channel reliability. So we assume that all the channels are reliable and only the processes gets failed, not the channels. And the next assumption is authenticated versus non-authenticated messages. With unauthenticated messages, so the faulty process relays a message to the other process. When a faulty process sends a message to other process, it may forge the message from other one, or otherwise it can tamper with the content of the received message before relaying it. So it may happen in unauthenticated messages. So the unauthenticated messages are also called as oral messages or unsigned messages. When a process receives a message, we don't have any way to verify its authenticity. Whereas if we go with authentication techniques like digital signature, so in case if the faulty process sends a forged message or a tampered message, the recipient can easily detect such type of forgery or tampering. And the next one is agreement variable. So the agreement variable can be a Boolean value, or it can be a multi-valued, or it can be an integer value. So the agreement variable may not be always, it should be an integer. It can also take a Boolean value. So with this we have concluded the assumptions what we have made in agreement problems. Then we move on to problem specification. So we have three types of problems: Byzantine agreement, consensus problem, and interactive consistency. So what is Byzantine agreement? So here we have the single source. Only the single source has an initial value. We have n number of processes, but only one process has an initial value. So what are the definitions what we have made in Byzantine agreement? The first one is agreement, that is, since we have only one initial value, all the non-faulty process must agree with that initial value. It should be same. The second one is validity. So if the process is non-faulty, then the agreed values must be the same as the initial value of the source, whereas the source should not get failed in the middle. And termination, each non-faulty process must eventually decide on its value. So that's about Byzantine agreement. The next one is consensus problem. Here all the processes are having its own initial value. So how we made the agreement means all the non-faulty processes must agree with a single value. Even we have multiple values, we have to agree with a single value. Here how we go with the validity means, so if all the non-faulty processes have the same initial value, then the agreed upon value by all the non-faulty processes must be the same value. So that is, all the processes are having initial value and this value must be same for all the processes. And termination, each non-faulty process must eventually decide on a value. Third one is interactive consistency. Here also all the processes are having its own initial value. Then how we go with the agreement means all the non-faulty processes must agree with some set of values, that is some array of values. The array of values must be same for all the processes. So how we are validating this means, so if the process Pi is a non-faulty process and its initial value is Vi, then all the non-faulty processes must agree with that same value Vi in the ith element of the array A. This is the concept. Okay, that is, we are agreeing with the value Vi for the process Pi. So, for all the processes in the array, the ith element must contain the value Vi. So, if the process is a faulty process, then you can store any value in that array. So, termination, again, all the non-faulty processes must eventually decide on the array A. So, overview of results on agreement. So, where F denotes the failure prone processes and N denotes the total number of processes. So, in failure mode, we are considering no failure, crash failure and Byzantine failure. And what is happening in synchronous system and what is happening in asynchronous system. So, we have separated the things and we go with both the types, message passing system as well as the shared memory system. So, if the processes are not failed, then easily you can attain the agreement. And in synchronous system, you can attain a common knowledge also. Whereas in asynchronous system, you can attain concurrent common knowledge. Here also agreement is possible. Second failure mode, that is a crash failure. Here also, in synchronous system, agreement is attainable, but the condition is f should be less than n. So here you have to move with f plus 1 rounds to make a final agreement. Whereas in asynchronous system, the agreement is not attainable, it is not possible. And the third failure mode is Byzantine failure. So in synchronous system, agreement is attainable, but the value of f should be less than n minus 1 by 3. And here also we need f plus 1 rounds. Whereas in asynchronous system, again the agreement is not attainable. So in a failure-free system, the consensus can be attained in a straightforward manner. So we may see with some variance, that is reliable broadcast, K-set consensus, epsilon agreement and the renaming. And this chart shows the types. So that is in asynchronous system, we have two types, message passing and shared memory. Under message passing, we have K-set consensus, epsilon consensus, renaming and reliable broadcast. And for the shared memory, again we have K-set consensus, epsilon consensus and renaming. And for shared memory, we have consensus. Okay. So that's about